Hey, my amazing AP Chem students. This is our second video about IMFs. I'm currently on page 10 of our notes. So please, a big important part of this is that you are following along with your notes and you are writing in your notes as we go. Okay, so I don't want you just listening to the video, I don't want you just watching the video, I want you to be taking notes at the same time. Okay, so during class, we talked about the three main types of IMFs: London dispersion, dipole-dipole, and hydrogen bonding. Okay. Now, a couple of things that I need you to know. First off, in general, and there are exceptions to this, and you will see exceptions on the test, in general, the strength of IMFs, the highest strength one is hydrogen bonding, then it goes dipole-dipole, and the lowest strength one is London dispersion. But if a molecule is large enough or has a shape that's conducive, the London dispersions can get really strong, and sometimes they can even outweigh a dipole-dipole or a hydrogen bond. Okay? So here's what's going on. When we have London dispersion, the electrons inside these molecules, they temporarily gather like on one side of a molecule, right? So like if I have a molecule and there's electrons just all around inside this molecule, they're moving around for just a moment in time. What if most of those electrons end up gathering kind of like on that side? That creates a temporary dipole, right? We have this temporary point in time where the electrons are spending more time over here and they had less time over there, and so we get a partially negative side and a partially positive side. Well, if there's another molecule, okay, that happens to be close by, if this is positive, then all of the electrons over here are going to be attracted to that positive, and so the electrons will gather, and then it creates another temporary dipole where we get a partially negative side and a partially positive side. So now we get an IMF attraction. This is London dispersion. So there's an attraction between them, and that attraction is only temporary, and then it happens again, right? Like, oh, London dispersion occurs for a moment, goes away, occurs for a moment, goes away. And what we see is that there are two main things that affect the strength of this London dispersion. The first one is just the size of the molecules. Like how many electrons are there in this molecule? Because the more electrons we have, the greater likelihood that they might accidentally gather, and the more electrons can gather. Okay, so if we have a larger molecule, we increase the polarizability of the molecule. Polarized, like look, it got polarized. The electrons unevenly gathered for a moment, and it made it a polar, almost like a polar molecule for that moment in time. So the larger the molecule is, the more polarizable the electrons of that molecule. Okay? That would make a London dispersion force stronger. So the larger the molecule is, the stronger the London dispersion is. This is the big takeaway there. Intermolecular forces become stronger as molecules become larger. Okay? And the reason why, and this is the phrasing that I want you to use, for larger molecules, the electrons are more polarizable. It's easier for the electrons to polarize, to get gathered on one side. Okay, so if you're asked for a justification on a free response test and it shows you a sample, so let's say we got two containers here. We got C2H6 6. And then in the other one, we got C4H. Okay, let me think. What would this one be? 1, 2, 3, 4, 10. Okay. So there's a bunch of C2H6 molecules in this container, and there's a bunch of C4H10 molecules in this container. There will be IMF attractions between the molecules within their respective containers. They're both hydrocarbons. So if I have another C2H6 molecule and there's a bunch more in there, there is an attraction between the molecules, and it is London dispersion. Same thing here. If I have more C4H10 molecules, they're both nonpolar because they're hydrocarbons, but there still is an attraction between them, and that attraction is London dispersion. Now, these London dispersions are not equal in magnitude. C4H10 is a larger molecule, and so it has more polarizable electrons due to the fact that it is a larger molecule. So if I had to rank the strength of IMF for C2H6 and C4H10, the IMF strength is stronger in C4H10 and it is weaker in C2H6. There's a couple of characteristics that I'm going to describe in just a moment that relate directly to strength of IMF, the biggest one being boiling point. And so the stronger the IMF, the higher the boiling point. So if I was given 2 boiling points and I had to assign them to either C2H6 or C4H10, the higher boiling point would be going to C4H10, and the lower one would be going to C2H6, because the stronger attraction leads to a higher boiling point. Okay, so relative strength of dispersion force is affected by 2 factors. The first one is size, the other one is the shape of the molecule. So we just said that the larger the molecule, the stronger the IMF. Okay. Now, imagine I got 2 molecules here, and one of the molecules is looking like this. Carbon, throw some hydrogens on there. And then we're going to put another carbon right here. And then, okay. So this is C4, 1, 2, 3, 4, H, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, just like before, C4H10. But we have another molecule that also has the formula of C4H10, and it looks like this. Okay, and then we go okay, so do you see how this shape versus this shape? Okay, C4H10, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, yes. If there is a sample of this kind of molecule for C4H10, and there is an example of this kind of molecule for C4H10, they both experience London dispersion, but one is stronger than the other, even though they're the same size, right? They contain the same number and amount of atoms, and same type of atoms, same amount of electrons. Okay? The London dispersion that occurs within this sample is stronger than that one. And the reason why is because think of like a classroom that's like kind of square versus a hallway, which is long. If electrons are wandering around this classroom, if we have students wandering around this classroom, they might get like temporarily bunched up over here, but they're not all that far away from the other side of the classroom. Okay? And so for there, that we create a dipole, but it's not nearly as strong as if we create a dipole over here. Because imagine we get all the electrons way over here, and so they're really far away from the other end of the molecule, and that's a larger dipole. That's a more uneven distribution of those electrons. So when we get these long hallway-shaped molecules, they create stronger temporary dipoles, which results in an overall stronger London dispersion attraction. Okay. So the longer the molecule is, the greater the London dispersion. The more rounded, square, circular, like compact the molecule shape is, the weaker the London dispersion. Okay. This is an in general. In general, London dispersions are the weakest, and then it's dipole, induced dipole, ion induced dipole, dipole dipole, hydrogen bonding, ion dipole, ion ion. Okay. Now, our main ones, the ones that I think that you're going to see most often, are London dispersion, dipole dipole, hydrogen bonding, and maybe probably this ion dipole. Okay. But what I need you to know is that this list holds true until you get to London dispersion, and this is true for most of the time unless the molecule gets really big and or really long. Then the London dispersion can become really strong, and it can become stronger than many of those other IMFs. Okay. Let's talk about 3 things: boiling point, melting point, and vapor pressure. Okay? Boiling point, melting point, vapor pressure. All of these have direct relationships to IMFs. So, the relationship to IMF for boiling point is directly proportional. That would mean that the stronger the IMF is, the greater the strength of the IMF, the higher the boiling point. Or the weaker the IMF, the lower the boiling point. This is also true for melting point. The relationship is directly proportional. So when an IMF between the molecules is stronger, the melting point becomes higher. Okay. But the relationship between IMF and vapor pressure is inversely proportional. So when we have a strong IMF, the vapor pressure decreases. This is what vapor pressure is. Imagine that I have a container, okay? So let's get this container, and I have gases that are flying around this container. And when they hit the walls of the container, the force at which they hit the walls is the vapor pressure. The greater force that they run into the wall, the greater pressure of that vapor against the wall. Okay? So if these are flying around and they hit the walls of the container, that would be the vapor pressure. Now, what if we have a really strong IMF? Meaning like this molecule, this gas molecule or atom, it has an attraction to other ones. That pulls them together and like away from the walls of the container. So because when the IMF is stronger, the molecules don't hit the walls of the container as often, and they don't hit the walls of the container with nearly as much force. So that would lower the vapor pressure. The stronger the attraction between those gas particles, the lower the vapor pressure. All right, so I'm changing this one up. Instead of doing this, I want to ask you, if we had a sample of, yeah, let's do this. Okay, go to page 13, please. Okay, so pretend we have a sample of this molecule. That means that this molecule is in a container with a bunch of other molecules that are exactly the same as it. Okay, so what I'm wondering right now is we got what if I have another one of these? Okay, we can imagine the hydrogens on there. Great. There's another one of these molecules. There's multiple of these molecules in a container. And so there are attractions between those molecules. Okay? So let's identify really quick. This molecule is polar. We get asymmetry there. Okay? And so when we have two polar molecules, what are the IMFs that we'd get? We'd get London dispersion because it's two molecules. We'd get dipole-dipole because they're both polar. They're both polar. And we would also get hydrogen bonding because look, I have a hydrogen bonded to a fluorine, oxygen, or a nitrogen, and the other molecule has a lone pair. So there's hydrogen bonding. C3H8, oh, a hydrocarbon, so it's nonpolar. So we would only have London dispersion. Okay. There are more types of IMFs, and there are stronger IMFs for this molecule compared to that molecule. So what would that mean for boiling point, melting point, and vapor pressure? Okay. If I am comparing these two things, this one would have a higher boiling point, and this one would have a lower boiling point. Now, what about melting point? Higher melting point, lower melting point. What if we get to a place that both of these are gases? Like we add enough energy, they're both gases. In that situation, we'd have a lower vapor pressure and we'd have a higher vapor pressure. Okay? Now, what if I told you that one of these is a liquid and one of them is a solid? Okay? So one's a liquid and one's a solid. Well, solids, the molecules and atoms are closer together when compared to the liquid, and then they're the furthest away in a gas. So in general, IMFs are much stronger in solids, a little bit less in liquids, and then they're the weakest when it's a gas. So if we had this information that one was a solid and one was a liquid, this one would probably be the liquid. And this, or sorry, for students, dyslexic teacher. This one would be the solid, and this one would be the liquid. Okay, nice. I want you to hit pause and try this one, and then we're going to come back and see how you did. Okay. Alrighty. Right away, I see that they're both polar. Polar, polar. Okay, and just a heads up, I've seen this quite a bit on the AP Chem test, where they just write this hydroxyl group, because it's hydroxide, where they just write OH, and I need you to know and remember what they mean is like that oxygen is bonded to the hydrogen, and there are lone pairs. Same here, there's lone pairs on this OH as well, okay? So if this molecule is in with a sample of itself, it would have London dispersion. They're both it's polar. It and another one of itself. So dipole, dipole, and hydrogen bonding. Okay. Now this one, London dispersion, dipole, dipole, and hydrogen bonding. But the IMFs are not equal because the London dispersion is stronger for one of these than the other. So the London dispersion is stronger for this molecule because it is bigger. It has more polarizable electrons due to the fact that there's more electrons and the size of the molecule is larger. Great. That means that even though they both have London dispersion, dipole, dipole, and hydrogen bonding, the London dispersion is bigger for this molecule than for that molecule. Also, there's more hydrogen bonds that can happen with this molecule than with this molecule. There's only really one site for hydrogen bonding on this molecule, but there's two sites for hydrogen bonding on that molecule. So for both those reasons, the London dispersion and the hydrogen bonds are stronger in this one than compared to that one. Okay. Okay. So, what would we see then? We would see, oh, sorry, I didn't mean to have another line on this one. So what would we see? We would see a lower boiling point and a higher boiling point. We would see a lower melting point, and we would see a higher melting point. We would see a higher vapor pressure and a lower vapor pressure. What if one was a liquid and one was a gas? I think it's actually way more likely that they're both solids, maybe a liquid and a solid. So let's do that. Let's say one's a liquid and one's a solid. So in that scenario, we go, oh, this one had the stronger IMF, so that's going to be our solid, and the other one's going to be our liquid. Okay, good. Alrighty, everyone. On page 12, we have this phrasing, and I've seen it quite a bit, so just a heads up. Isomers. Isomers are two different molecules with the same chemical formula. Okay, so this is an example of an isomer. Both of these molecules have a formula of, let's count it, so 1, 2, 3, 4, 5, 6, 7, 8, C8, and then H, and 18, did I count that right? 16, 17, 18, yeah. Okay, so these are not the same molecule. They are isomers of each other. They both have a chemical formula of C8H18. they're both hydrocarbons. So they would experience, if they were in a sample of themselves, so I'm not talking about the IMFs that would occur between them, not that it really matters on this one, but if this one was in with a bunch of other molecules that were the same as it, it would only have London dispersion. Same with this one, it would only have London dispersion. But remember how size and shape play into it? They're the same size, they got the same number and types of atoms, but this one has that long hallway shape, where this one has, it's more compact, right? Like circular square. And so the London dispersion would be stronger for this isomer than compared to that isomer, right? So two chemicals shown below, octane on top and isooctane, on bottom, are isomers. Which one would you expect to have a stronger intermolecular force? I would expect this one to be stronger. Okay, good. All right, everyone, so here's the plan. We, next class, we are going to spend a little time talking about ion dipole forces and their difference in strength and orientation around molecules. And we're going to talk about ion-induced dipoles a little bit more. And then I have a game for us to play where we're going to be identifying IMFs and talking, like registering which one has higher vapor pressure and boiling point and melting point and that kind of stuff. So thank you again, everyone, for your hard work. I want to see next class when I'm looking at your notes that we have these filled in. So please, please, when you're watching the videos in the future, I need you to be looking at it and filling your notes as you go.